So if Bob's talk was a high-level sketch, then my talk is sketchy. Uh, my goal here is to give you an idea of a problem we're starting to work on and our intended approach, but maybe you'll email me later and tell me how I'm wrong. Uh, Working on this problem of constraint compliance for a while, and like Bob showed, we've worked on different parts, but recently we've really been focusing on this idea of when an agent has multiple constraints and it has abstract specifications, and there's this joint problem of figuring out how to integrate constraints and do your task. What do we do there? And so we're focusing right now on this problem of conflict mitigation. In some previous work, we assumed that an agent might have had coherent constraints and that it had enough knowledge in the system to be able to deal with them. But now we're trying to think about when that's not true. So sometimes, well, realistically, you cannot foresee every combination of constraint instantiations and train everything beforehand. You might have incomplete knowledge of some of your constraints. That is, they're only expressed abstractly, or constraints in the world, they are sometimes inherently of different types, and it's not like there's a one-size-fits-all solution. The external world, it's going to present these various kinds of constraints, and you need to recognize these different types and apply the right kind of knowledge to interpret them. And this can get harder when multiple different constraints bear on a single decision. So I want to give some examples of humans handling constraints. We might have traffic laws. So traffic laws, ostensibly, they're presented as rules, hard rules. But then maybe when you're selecting what television to buy, you might have some features you want to satisfy, but beyond that, maybe you just look at the explicitly listed prices. You have other constraints like manners, and this gets a little bit more difficult. Sometimes you can think of manners as these things that have like implicit or uncertain costs. Other times you might think of them as rule-like, but maybe there's a degree of slack. How strictly are you expected to follow them? And sometimes you're not even sure what the actual constraints are, but you have a good example to follow of someone else who knows how to integrate constraints into their behavior on a task. And so, in general, I'm trying to use these examples to illustrate to you that our knowledge of constraints is incomplete. And that's what's going to make integration difficult. Let me carry this further. If you're driving really fast to get to the hospital, you're able to do some kind of reasoning in your head to know to ignore certain traffic laws. Now, I'm not saying ignore traffic laws, but this is the kind of difficult decision that involves thinking about different types of constraints. This is another way of saying the same thing. I just want to emphasize that the problem of applying constraints, it's a problem of using the knowledge that you actually have available. A contrast to the kind of approach we're talking about would be if you only assumed one form of knowledge for constraints, like if you had to fit every constraint into a cost-oriented formalism, or you could only really represent the constraints out there in the world as rules. And our hypothesis is that by using all available knowledge over a broader decision space, we're going to get more aligned outcomes and more legible decisions, sensitive to the specifics of a situation. So to explore this, we've been looking at a couple of situations where, among other constraints, we're assuming a motivating constraint that an agent should preserve human life. But gosh, that's really abstract. It's hard to implement that in a specific situation. So we've been inspired by scenarios from the Naval Postgraduate School. Basically, they have missions where they're kind of saying, this is how you fulfill that constraint, right? What does it mean to preserve the human life of a sailor who's overboard? Well, we have a mission for that, actually. They spell out, here's how you do search and rescue. The problem is, we can imagine that in the real world, there are other goals that also need to be fulfilled, like returning to port. And there are other constraints that need to be taken into account, such as fuel consumption. And so that makes generating behavior more difficult, right? You can't just follow this mission. You have to be sensitive to the other things that are going on. And there's several different ways to generate behavior that tries to take all of this into account. A common approach is to encode many aspects of a situation as costs, and then train a policy. So you might think of something like, suppose losing a sailor costs X. Well, you could have a simple utilitarian agent, and it might assign costs to things such as failing to reach the port that's your destination. It might assign costs to things like fuel consumption. The problem is the following perverse behavior could result. What happens if the ship is getting low on fuel, but then it spots the sailor? Well, it could be the case, based on the available fuel, these encoded costs, a simple model might find that even though you've spotted that sailor, you know what, it's worthwhile to turn around and prioritize going back to port. Now, you and I might realize that at the very least, it's sort of like the cost is different when you actually know the sailor is alive and you can see them. And so that might be an example of where having tried to force everything into this cost formalism in advance is going to fail you. Some people might even feel like assigning a cost here, pardon, doesn't really represent a human-like knowledge of a duty, such as no one left behind. And so the point here is that if you can integrate these different ways of thinking of the constraint, you might get more aligned behavior. Now, I want to consider another example. In this example, we have a horrible situation. We want to preserve human life, but 2 merchant ships are being attacked at once by speedboat pirates, and there's only one potential responder. We have a duty to protect, and from the Naval Postgraduate School, we have a good specification of what it means to have behavior that respects that constraint. You're supposed to defend a merchant. We have 2 instances of this duty at the same time, and we just can't move fast enough to pick more than one. So we can imagine encoding simple rules for what to do that would resolve this problem. For example, intervene for the closest ship, or intervene for the highest value ship. And those might actually generate reasonably aligned behavior in some cases, but they could also ignore important details. What if one ship has many more crew members? Now, you can imagine an agent doing lots of reasoning to determine which ship it really has a greater duty to defend and playing out a lot of simulations, but really, you have kind of the same duty in both cases, and it's going to be difficult to compare all these little details. I think this is a situation where we could assume an agent would have a lot of statistics from previous attacks, and it might be reasonable that a trained up policy that's going to have a good idea of how to respond. It could quickly be sensitive to this large trove of previous attacks with like compiled policy knowledge. And probably it would be sensitive to things like, the probability I'm going to successfully defend is going to depend on how far away the boat is. Maybe how important it is to defend is going to be dependent on how many crew members are on the ship. And so even though you have this rule-like knowledge of how to actually carry out a defense, you still have to weigh which defense to prioritize, and that might be better done with utility style knowledge. So this is an example of bringing these different kinds of knowledge of constraints to bear on a single problem. Sorry. But it can get even more complicated. Let's change the knowledge the agent has a little bit. So what if the agent recently saw a demonstration of new water cannon defenses and knows one of the ships has that defensive ability? Well, the trained utility estimates we might have learned from the statistics or past attacks, it doesn't really hold here. The utility of helping out this bottom ship that has these defenses, it might be lower than what our old policy estimates would say, because they could maybe fend for themselves for a while. And so based on this example knowledge, right, I'm assuming the agent it saw a water cannon demo in the recent past. if it can bring that example to bear on its situation, it might be able to choose instead to help the other ship. And so this would be an example where we're using meta reasoning that's combining an example and utility knowledge to make a decision. And the idea is if you have that capacity to bring these different kinds of constraint knowledge to bear, you might get better results. And in this example, you may be able to save both ships. Now, the requirements, and like we're still working on this, but the requirements that we seem to be arriving at for any approach to reasonably deal with this problem is you're going to have to integrate a variety of constraint knowledge sources and types into your agent's knowledge, such as examples, rules, costs, maybe abstract virtues. And what that means is you need an expressive knowledge representation that can match the diversity of constraint knowledge present in the world. And there's actually some other prior work emphasizing this requirement. You also need to have this real-time ability to determine that you have an incompleteness in your current knowledge, or that there's a conflict you need to resolve. If you have an example saying one thing and utility knowledge saying something else, you have to be able to respond to that. And this needs to happen in real time. And so the important aspects of the approach we intend to take in Soar is we're going to have conflicts and knowledge incompleteness explicit. And we expect meta reasoning to guide decision making in those cases. And an important effect of that is we're going to be able to tell why an agent chose what it chose. And it really looks like Soar is going to be able to support this as part of its real-time reasoning. So the nuggets here is this really looks like it's going to play into Soar's strengths. It's about bringing all available knowledge to bear on a problem. And unlike some works, it doesn't depend on us taking like a moral stance at design time to champion an ethical frame. And I believe that by making this recognition of conflicts explicit, we're going to have more legible reasoning behind these constraint-related decisions. But there's a pull here, and it's that, gosh, it's a lot easier when you can simplify the problem by prescribing the form of constraint knowledge in advance, right? If you can shove everything into costs, gosh, utility formalisms are great. But I just don't think that's the full problem. Willing to accept some questions. I was expecting something from Joe McDonald based on the previous question.
I've got a question for you.
Go ahead.
You were mentioning a lot about constraints and how to operate in constraints, and I think you went over this in your talk a little bit. But I just wondering if you could expound on it a little more. But it seems to me that the constraints, like having to drive, certain laws when we drive in traffic, whatever, the constraints are what kind of force us to learn. When we're in a library, we kind of learn at our leisure, and sometimes we retain, sometimes we don't. But if our lives depend on it, or if something's going to hurt me more unless I learn how to make it stop, it does kind of force the agent to figure something out. I'm just wondering with the current system that you're showcasing, how that could in some ways be an advantage. And forgive me if that's kind of how you presented it, but that was just a question that I had.
Huh. I almost want you to repeat it. So, unfortunately, the approach we've taken to learning specifically, I would say, doesn't have the features that you're describing. I actually agree with you, but we've been imagining that you do have some external supply of constraints given to you.
Hmm.
So it's not that I think you're wrong, it's just unfortunately we haven't been pursuing the kind of synergy you're talking about.
Oh, okay.
But I mean, that I'm basically saying like, yes.
No, it was very fascinating. I actually thought that was how it worked, but I wasn't sure. But that answers my question. Thank you.
So the thing we're trying to learn in most of what we're doing is really how to apply these abstract or incomplete constraint knowledges to a situation. And so there's a lot of details about how to respond to the situation that need to be figured out, and less so on acquiring the constraints themselves. Maybe we get more knowledge about them, but it's not like we're learning them.
Gotcha.